All right, let's dive in. We're going to demystify the invisible force that powers pretty much everything in our modern lives: alternating current, or as you know it, AC.
It's funny. You probably don't even realize it, but we're all living in two completely different electrical worlds. Those simple circuits with batteries you learned about in science class, that was direct current, or DC. But the real world, the one that powers our homes, our cities, our entire lives, that all runs on the dynamic, powerful world of AC, coming straight from our wall sockets.
So what's the big difference here? Well, it really boils down to two things: polarity and frequency. Think of it like this. DC is a steady one-way street. The current just flows in one direction. Nice and simple. But AC? Oh, AC is a super fast two-way highway. The current flows one way, then flips and flows the other way, back and forth, dozens of times every single second. And this frequency? It's not just some number on a spec sheet. It has huge, real-world consequences. I mean, the source material gives this perfect example. Somebody brought their hairdryer from the US, which runs on 60 hertz, over to India, where everything's on a 50 hertz system. The second they plugged it in, poof! The appliance tried to suck way too much power, and the entire house fuse just blew, instantly. Okay, so this constant back and forth, this switching from positive to negative, brings up a really interesting puzzle. I mean, think about it for a second. If the current spends exactly half its time flowing one way and the other half flowing the exact opposite way, what happens when you try to average it all out? Yup, it's zero. Over one full cycle, that positive half completely cancels out the negative half. It's like taking one step forward and then one step right back. On average, you haven't actually gone anywhere. And, this creates a major problem when you try to measure it. And that right there is what we call the zero average problem. If you were to take a standard DC voltmeter, the kind you'd use for a battery, and plug it into your wall socket, it would just read zero, nothing. So how in the world do we measure and use a power source that on average looks like it's not even there? Well, the way we solve this is by completely changing the question. Instead of trying to find the average, we ask something much smarter. What amount of AC gives us the same effect, the same amount of work or heat as a DC current? So, picture this. You've got two identical light bulbs. The goal is to figure out the AC voltage that makes one bulb glow exactly as brightly as the other bulb, which is powered by a DC voltage we already know. And that effective value has a special name, the root mean square, or RMS value. And this is the standard. It's how we all talk about AC voltage. So when you hear someone say 230 volts in India or 120 volts in the US, what they're really talking about is the RMS value. It's the DC equivalent in terms of pure power. And what's really cool is that the name, root mean square, is basically the instruction manual for how you calculate it. Seriously. First, you take the AC wave values and you square them, which gets rid of all the negative numbers. Then you find the mean, or the average, of all those new positive values. And finally, you take the square root of that average. It's just a really clever mathematical workaround for that whole zero average problem. Now, luckily for all of us, for a standard AC sine wave, we don't have to do all that math every time. It boils down to this really simple, elegant relationship. The RMS value, the number we actually care about, is just the peak value of that wave divided by the square root of 2. It's a super clean and direct way to get the number we need. Okay, so we figured out how to measure AC. Now for the fun part. Let's see how it actually behaves when it gets into a circuit. We're going to look at how it interacts with the three absolute cornerstones of electronics: the resistor, the inductor, and the capacitor.
See, in the simple, predictable world of DC, voltage and current are best friends. They're always in sync. But in an AC circuit, things get a little more complicated. They don't always move together. Depending on what component they're flowing through, the voltage and current waves can get, well, out of step. One can start leading or lagging behind the other.
Let's start with the easy one, a simple resistor. All a resistor does is fight against the flow of current. And frankly, it doesn't care which way that current is going. So with a resistor, AC behaves exactly how you'd think. The voltage and current are perfect partners. They rise together, they fall together, they hit zero at the exact same time. We say they're in phase, with a phase difference of, you guessed it, 0 degrees. But then we get to an inductor. An inductor stores energy in a magnetic field, and that field really doesn't like it when the current changes. It fights back. Because of this, the voltage has to build up first to kind of force the current through, giving the voltage a head start. So, the voltage wave hits its peak a full 90 degrees before the current wave even gets there. We say the current lags behind the voltage. And then we have the capacitor, which stores energy in an electric field, and it does the exact opposite. A great way to think of it is like a tiny, super fast-charging battery. The current has to flow into it first to build up a charge, right? Only then can the voltage across it start to rise. So in this case, the current is the leader. It hits its peak a full 90 degrees before the voltage does, which means the voltage is the one that's lagging. So this opposition to AC flow from inductors and capacitors is so special, it gets its own name. It's not called resistance, it's called reactance. Now, it's still measured in ohms, just like resistance, but here's the key difference. It's a dynamic opposition. It actually changes depending on the AC frequency. And this right here is what makes AC circuits so much more powerful and versatile than their simple DC cousins. You see, these phase shifts, they're just some weird electrical quirks. They are absolutely fundamental to, well, everything, from how you tune a radio to how we manage our massive power grids. Think about it this way. Resistors, inductors, and capacitors are like the basic alphabet of electronics. On their own, they're pretty simple. But what happens when you start combining them? When you start building words and then sentences and then entire electronic languages? Well, that is where the real magic of our modern world truly begins.